Well, hi. We're going to talk about a new concept called torque. Torque has to do with rotation. Suppose I'm looking down on the top of a door. So here is a door. Over here is where the hinges are, and we're looking down on the door. Now, if I want to open the door, I have to push on it with some force. Or maybe I pull on it. So suppose I apply a force like this, and that will open the door. But I can think about that force as having components. It has a component F parallel, it's parallel to the door, and a component F perpendicular that's perpendicular to the door. And notice it's really only this component, I'll call this angle theta, it's only this component, the perpendicular component, that can really open the door. This component is just pulling on the door and pulling on the hinge. And you can't open a door by pulling on the hinge. Only the perpendicular component, which turns out to be, if I draw it over here, F perpendicular is F sine of that angle theta. That's the only part of the force that's really helping me open the door. Also, it matters where I push on the door. If I push over here, it's easier to open the door than if I had applied the same force over here. Now it's much harder to open the door. If I push over here, it's really, really hard to open the door. We've all been somewhere where we pushed on the wrong side of the door, going into maybe a mall somewhere with glass doors, and we didn't know which side to push on, and we pushed on the wrong side, and it's really hard to open the door. So it matters how far away this force is. So this distance, we'll call it R, matters as well. So the ability to rotate this door depends on how big the force is, how hard we push, the angle, theta, and how far away the force is. All of those are captured in this idea of torque. And the torque that this force applies is given by the distance R, F, times the sine of that angle theta. This is the torque. This is, I'm using the symbol tau. That's the Greek letter tau for torque. There's no absolutely agreed on symbol for torque. Some books use tau, some use an uppercase gamma, some use T. I happen to use tau. So this concept torque is a measure of the ability of this force to cause rotation about some axis. Notice in this case the axis was these hinges. So by definition we're going to call this a measure of the ability of a force to cause rotation about some axis. Notice it's not a force. It encapsulates more than a force. So it's ability of a force. So please don't say a torque is a force. Torque's not a force. It's a force and other stuff. So it is a force at a distance and an angle. It's all of these things. It's a measure of how well this force can cause rotation, and that's torque. It has units of meters for this, newtons for that, so it has units of newtons times meters. Now earlier in the course, when we were looking at energy, we saw a newton times a meter was a joule. We don't do that here because a torque is not an energy. So even though when we're dealing with energy and work, newton times a meter was a joule when we were dealing with work and energy, for torque, we just call it a newton times a meter. In the British system, this would be a foot-pound is what is used if you're a mechanic and working on a car in the British system of units. It's foot-pounds. In the metric system, or the SI system, it's a newton times a meter. Now, this isn't the only way to think about this. So when I introduce this here, I introduce the idea that only this perpendicular force, this perpendicular component, was useful in opening the door. There's another way people often think about this that turns out to be mathematically equivalent. Oh, by the way, please memorize this. So let me show you another way of thinking about this. So not all objects are as easy to think about as this door. So here's this weird shaped object. I'm going to put an axis here, and I'm going to apply a force over here, and which will tend to rotate this jelly bean type object around this axis. Sometimes people think in the following way. Often engineers do this. They'll draw a line in the direction of the force, and they'll draw a perpendicular to that line, and they'll call this distance r perpendicular, something called the lever arm. And when you think about torque this way, now you can think about the entire force rather than this component, but not the entire distance. By entire distance, notice up here the distance from the axis all the way to the force. That would be this distance. Here's where the force is being applied. This would be what I just called the entire distance. Now I'm saying, no, not that entire distance, just this perpendicular distance called the lever arm. If you take that distance times the force, you also get torque. Torque is r perpendicular F, where as long as this r perpendicular is the lever arm, and that gives you the same answer, because this r perpendicular is this r we had before times the sine of theta. So we've got three ways now of thinking about torque. You can think of torque as this perpendicular component of F times r. That gives you the torque, because that F perpendicular is F sine theta. You can think of it as the lever arm, r perpendicular times F. That works. Or you can think of it as just r F sine theta. All of those give you torque. They're all mathematically equivalent. So let me do a couple of examples for you. Suppose I have, again, a stick, and there's an axis here. You always have to know where the axis is. The torque does depend on the axis. It depends on where the hinge is. And this is 3 meters long, and I apply a force at the end, just to make it easy to think about. This is a 30-degree angle, and it's a 20 Newton force. Now the torque will just be RF sine 30. It's very straightforward to start with. So R, when we're doing RF sine theta, that R is the entire distance from the axis all the way to where the force is applied. So this is 3 meters, 20 newtons, sine of 30. That is 30 Newton meters. But note the following. What if the force had been like this? 30 degrees. 3 meters. Same axis. Now I'd get the same answer. Torque would be RF sine 30, would be 3 meters, 20 newtons, sine 30. That would again give me, let's see, 20 times 3 is 60, but that's wrong. Oh no, that's right, times the sine of 30 gives me 30. 30 Newton meters. They gave you the same answer, but they're obviously different, because this is going to rotate the stick that way, counterclockwise, and this is going to rotate the stick clockwise. So we need to distinguish those. So we have two ways of doing that. When it rotates the stick counterclockwise, see the hands of a clock, that's opposite the way the hands of a clock would rotate around this axis. So we actually sometimes just say counterclockwise and clockwise. But we also need a mathematical way of distinguishing them. And mathematically, we say counterclockwise is positive, and we say clockwise is negative. The reason we do that is rotation counterclockwise is toward positive angles in a Cartesian coordinate system, and toward clockwise is toward negative angles in a Cartesian coordinate system. So this we would call a positive torque, and this a negative torque. We could have thought of, well, no, I'll just leave it at that. Let me do one more example for you. Got a stick with an axis here. 0.20 meters here, 0.75 meters, F1, no, call that F2, is 30 newtons at 60 degrees. F1 is 20 newtons at 55 degrees. And I just want to find the net torque. So tau 1 is just F1 x1, or this is my x1, sine 55. So that's just 20 newtons, 0.75 meters, sine 55. That's 8.19 Newton meters. And notice if my axis is here, pushing out there would rotate that way. That's counterclockwise, so that's positive or counterclockwise. Tau 2 is F2 x2 sine 60. This is x2. That's 0.2 meters, 30 newtons, sine 60. But if my axis is here, pushing out here would rotate clockwise, so that's negative. So this is minus 5.20 Newton meters. Net, since I asked for the net torque, net always means sum in physics, is tau 1 plus tau 2. Oh, and this one's, it's minus, so that's clockwise, is 8.19 Newton meters minus 5.20 Newton meters is 3.00 Newton meters. And since it came out positive, that means the net result will be counterclockwise. So this will get you started. There's more to torque, and we'll see more of that as we prepare for and do Friday's class.